To source a 700 amp DC contactor, single pole, suitable for switching 700 amps at 270 volts DC, several manufacturers and distributors can be considered. The coil voltage is flexible, making the search somewhat easier. Let's examine potential manufacturers. Eaton offers PK's own series contactors. Schneider Electric features TESA's D-series contactors. ABB provides AF contactors, and Siemens produces Series 3 RT contactors. Each of these manufacturers has lines of contactors that may meet the specified requirements. Next, consider distributors. Grainger is a widely known industrial supplier. ESCO, Allied Electronics, DigiKey, and Newark are also options for finding the appropriate contactor. When searching, knowing specific model numbers can be helpful. For Eaton, our possible model number is PK0-700-1. Schneider Electric offers the Elcone F700. ABB provides the F96-30-7. Siemens has the 3RT1075-6AP0. These model numbers should be verified against the specifications needed for the application. The contactor should have a pole count of 1, a current rating of 700 amps, and a voltage rating of 270 volts DC. The coil voltage can be variable, such as 24 volts DC or 120 volts AC. Several additional factors should be considered during the selection process. Firstly, confirm that the contactor is compatible with the specific application requirement. This includes the type of load being switched, the frequency of operation, and any environmental factors that may affect performance. Secondly, think about the contactor's life expectancy and maintenance needs. Different contactors have varying life expectancies, and some may require more maintenance than others. Thirdly, it is important to check the availability of accessories. These accessories can include auxiliary contacts, surge suppressors, and terminal blocks. These accessories can enhance the functionality and reliability of the contactor. Finally, it is advisable to consult with the manufacturer or distributor for technical assistance. They can provide valuable insights into the selection process and help ensure that the chosen contactor is the best fit for the application. Contactors are electromechanical devices used to switch electrical circuits. They are similar to relays but are typically used for higher current and voltage applications. A contactor consists of a coil, which when energized, creates a magnetic field. This magnetic field attracts a movable armature, which in turn closes or opens a set of contacts. The contacts are the part of a contactor that carries the electrical current. Contactors are used in a wide variety of applications, including motor control, lighting control, and power distribution. They are an essential component in many electrical systems. The selection of a contactor involves understanding several key specifications. The voltage rating of a contactor indicates the maximum voltage that the contactor can safely switch. It is crucial to select a contactor with a voltage rating that is equal to or greater than the voltage of the circuit being switched. The current rating of a contactor specifies the maximum current that the contactor can continuously carry without overheating. Selecting a contactor with an adequate current rating is vital to prevent damage to the contactor and the circuit. The pole count refers to the number of independent circuits that the contactor can switch. A single pole contactor can switch one circuit, while a double pole contactor can switch two circuits, and so on. The coil voltage is the voltage required to energize the contactor's coil. It is important to select a contactor with a coil voltage that matches the available control voltage. The life expectancy of a contactor is the number of operations that the contactor is expected to perform before it needs to be replaced. Contactors are mechanical devices and are subject to wear and tear. The life expectancy of a contactor is affected by factors such as the frequency of operation, the type of load being switched, and the environmental conditions. The maintenance requirements of a contactor include regular inspection and cleaning. Contactors should be inspected regularly for signs of wear and tear. The contact should be cleaned to remove any dirt or debris. The terminals should be tightened to ensure a good electrical connection. Accessories for contactors can include auxiliary contacts, surge suppressors, and terminal blocks. Auxiliary contacts provide additional contacts that can be used for control or indication purposes. Surge suppressors protect the contactor from voltage surges. Terminal blocks provide a convenient way to connect wires to the contactor. When selecting a contactor, it is important to consider the specific application requirements. This includes the type of load being switched, the frequency of operation, and the environmental conditions. The type of load being switched affects the current and voltage requirements of the contactor. The frequency of operation affects the life expectancy of the contactor. The environmental conditions can affect the performance and life expectancy of the contactor. Consulting with the manufacturer or distributor for technical assistance can provide valuable insights into the selection process and help ensure that the chosen contactor is the best fit for the application. Technical assistance can help in understanding the specifications of the contactor, selecting the appropriate accessories, and ensuring that the contactor is installed and operated correctly. The National Electrical Code, or NEC, provides guidelines for the selection and installation of contactors. NEC Article 430 covers motor circuits, including the selection of motor starters, which often utilize contactors. NEC Article 670 covers industrial machinery, which may also involve contactor applications. NEC Table 310.15b16, formerly 310.16, provide ampacity ratings for conductors, which is relevant to selecting appropriately sized conductors for the contactor's circuit. Ampacity is the current carrying capacity of a conductor. It is important to select conductors with an ampacity that is equal to or greater than the current being carried. Proper conductor sizing is crucial for safe and reliable operation. Overheating of conductors can lead to insulation failure, which can cause short circuits or fires. NEC Section 110.3b requires that electrical equipment be installed and used in accordance with the manufacturer's instructions. This includes contactors. The manufacturer's instructions provide important information about the installation, operation, and maintenance of the contactor. Failing to follow the manufacturer's instructions can void the warranty and may lead to unsafe conditions. NEC Section 408.55 covers the overcurrent protection of panel boards. Panel boards are used to distribute electrical power to branch circuits. Contactors are often used in panel boards to control branch circuits. Overcurrent protection devices, such as circuit breakers or fuses, are used to protect panel boards from overloads and short circuits. It is important to select overcurrent protection devices with the correct rating for the circuit being protected. NEC Section 430.52 provides guidelines for the overcurrent protection of motor circuits. Motor circuits are often protected by fuses or circuit breakers. The overcurrent protection device should be sized to protect the motor from overloads and short circuits. NEC Section 430.83 covers the overload protection of motors. Overload protection devices are used to protect motors from overheating. Overload protection devices can be thermal overloads or electronic overloads. Thermal overloads are devices that trip when the motor's temperature exceeds a certain level. Electronic overloads are devices that monitor the motor's current and trip when the current exceeds a certain level. The interrupting rating of a contactor is the maximum short circuit current that the contactor can safely interrupt. It is important to select a contactor with an interrupting rating that is equal to or greater than the available fault current at the point of installation. The available fault current is the amount of current that would flow in a short circuit condition. It is typically determined by a short circuit study. A short circuit study is an engineering analysis that calculates the available fault current at various points in an electrical system. It is important to conduct a short circuit study to ensure that the electrical equipment is adequately protected. The withstand rating of a contactor is the maximum short circuit current that the contactor can withstand without damage. It is important to select a contactor with a withstand rating that is equal to or greater than the available fault current at the point of installation. The short time current rating of a contactor is the maximum current that the contactor can carry for a specified period of time. This rating is important for applications where the contactor may be subjected to short-term overloads. The control voltage of a contactor is the voltage required to operate the contactor coil. It is important to select a contactor with a control voltage that is compatible with the available control power. Common control voltages are 24 volts DC, 120 volts AC, and 240 volts AC. The operating temperature range of a contactor is the range of temperatures within which the contactor is designed to operate. It is important to select a contactor with an operating temperature range that is suitable for the environment in which it will be installed. The altitude dating factor of a contactor is a factor that reduces the current carrying capacity of the contactor at higher altitudes. This is because the air is less dense at higher altitudes, which reduces the cooling effect of the air. It is important to consult the manufacturer's specifications for the altitude dating factor. The pollution degree of a contactor is a measure of the amount of pollution that the contactor is designed to withstand. Pollution degree 1 is for environments with no pollution or only dry, non-conductive pollution. Pollution degree 2 is for environments with occasional condensation. Pollution degree 3 is for environments with conductive pollution or condensation. The enclosure type of a contactor is a measure of the protection that the enclosure provides against environmental factors such as dust, water, and corrosion. Enclosure types are defined by NEMA standards. NEMA 1 enclosures are for general purpose indoor use. NEMA 3R enclosures are for outdoor use and provide protection against rain and sleet. NEMA 4 enclosures are watertight and dust-tight. NEMA 4X enclosures are watertight, dust-tight, and corrosion-resistant. The contactor's horsepower rating indicates the maximum horsepower of a motor that the contactor can control. Horsepower ratings are based on the motor's voltage and current requirements. The inrush current of a motor is the current that the motor draws when it is first started. The inrush current can be several times the motor's full load current. Contactors must be able to withstand the inrush current of the motors that they control. The full load current of a motor is the current that the motor draws when it is operating at its rated horsepower. The service factor of a motor is a measure of the motor's ability to operate continuously at loads greater than its rated horsepower. Motors with a service factor of 1.15 can operate continuously at 115% of their rated horsepower. The locked rotor current of a motor is the current that the motor draws when it is stalled. A locked rotor current is typically several times the motor's full load current. Contactors must be able to interrupt the locked rotor current of the motors that they control. When selecting a contactor for a specific application, it is important to consider all of these factors to ensure that the contactor is properly sized and will provide reliable operation. Consulting with a qualified electrical engineer can help ensure that the correct contactor is selected for the application. The engineer can perform calculations to determine the required current and voltage ratings, as well as the interrupting and withstand ratings. They can also consider the environmental factors and the specific requirements of the application. Maintenance practices for contactors include regular inspection, cleaning, and tightening of connections. Contactors should be inspected regularly for signs of wear and tear, such as cracked or broken parts, loose connections, and corroded contacts. The contact should be cleaned periodically to remove any dirt or debris. Loose connections should be tightened to ensure a good electrical connection. Regularly scheduled maintenance can help to extend the life of the contactor and prevent unexpected failures. Troubleshooting a contactor involves checking the coil voltage, the contacts, and the wiring. If the coil voltage is not present, the problem may be with the control circuit. If the contacts are damaged or worn, they may need to be replaced. If the wiring is loose or corroded, it should be repaired or replaced. Safety precautions should be taken when working with contactors. Always disconnect power to the circuit before working on a contactor. Use insulated tools to prevent electric shock. Wear safety glasses to protect your eyes from flying debris. Follow all applicable safety codes and regulations. Proper grounding is essential for electrical safety. All electrical equipment should be properly grounded to provide a path for fault current to flow back to the source. This helps to prevent electric shock and fire hazards. Grounding conductors should be sized according to the NEC. Surge protection devices can protect electrical equipment from voltage surges caused by lightning strikes or other events. Surge protection devices should be installed at the service entrance and at sensitive equipment. Harmonic filters can reduce the level of harmonic distortion in an electrical system. Harmonic distortion can cause problems with electrical equipment, such as overheating and premature failure. Power factor correction capacitors can improve the power factor of an electrical system. A low power factor can result in increased energy consumption and reduced system capacity. Energy efficiency is an important consideration in the design and operation of electrical systems. Energy-efficient equipment should be used whenever possible. Energy-saving measures can also be implemented, such as turning off lights when they are not needed and using occupancy sensors to control lighting.